So let's talk briefly about some of the consequences of what we've learned about heat. First, just a quick review. We know that heat is the motion of molecules and really corresponds to the store of kinetic energy in the molecules. And the temperature is the average kinetic energy of the molecules as they go zipping around. Well, there's a consequence to this. If you think about momentum, so we're going to back up a couple of weeks to when we covered momentum. All right. Now you got a molecule that's going along, hits the surface, boom, and bounces off of the surface. Right. Well, that requires momentum transfer from the molecule to the surface and so on. So if you put a molecule of gas in a balloon and you heat it up, it starts hitting the surface more and more and harder, and all of this is happening faster. And because of that, the balloon does what? The balloon expands, right? So you can actually inflate a balloon using air just by heating up the air, and the air makes the balloon inflate. And also makes it all lighter than the air outside the balloon, and balloons then will float, right? You can also disturb your nieces and nephews by taking their balloons and putting them in the freezer and having them shrink down a good bit, and then pull them out, and they'll go back out. All right, and this is all because these molecules are bouncing against the surface. All right. These molecules are bouncing because remember, it's their kinetic energy, their motion, that has them bouncing against the surface and putting pressure on the surface. Well, it turns out this is also true for solids. So when a solid heats up, it gets larger, it expands, and usually we think just in terms of linear expansion. Linear expansion is the increase in length along the long axis of something. You'll see bridges that are designed for this expansion where they have these expansion joints. You'll even see in some of the buildings in the science building, there are several expansion joints in the science building at Delta State. But bridges, you'll see these strips where this is meant so that when it gets colder and things get shorter, these things pull apart, right? And when it heats up, they go together more. Your goal is to have things set up so that at the coldest the bridge ever goes, you still have a safety margin, and at the hottest the bridge ever goes, you still have a little bit of a gap. I was in Switzerland during a time when we had a minor earthquake, a magnitude 2 on the Richter scale, and they had to tear down a bridge. And it wasn't that the bridge was damaged per se, but it was summer when the quake came about. The bridge was as long as it was going to be, and the valley the bridge spanned grew just a little bit wider. And because it grew just a little bit wider, the bridge was pulled to the very limit of its expansion joints, and the Swiss knew that come winter, when the bridge contracted and tried to get shorter, it was simply going to tear itself apart. All right. So here we have linear expansion. We're going to use this equation some just to get an idea of, well, how big it is. This is what runs a thermometer, by the way. You heat up the mercury, or modern thermometers, you heat up the alcohol in the thermometer and it expands because you've increased the temperature, right? So the change in length, delta L, is the coefficient of linear expansion times the length, the original length, times the change in temperature. Now in this case, the coefficient of linear expansion can usually be in degrees C or Kelvin, and it doesn't really matter since this is a change. Got to remember, 1 degree Celsius is exactly the same size as 1 Kelvin. So when we start talking about the change in temperature, the change in temperature is the same on both the Celsius and the Kelvin scales. Another aspect of this with the balloon is you can predict how much bigger the balloon will be in terms of its volume for a given pressure, and this is how much gas is in the balloon basically. T is the temperature. Again, this temperature has to be in Kelvin, and here has to be in Kelvin, right? And you can get that from the Boltzmann constant, which is joules per Kelvin. So if you want to work with the ideal gas law, you have to convert to Kelvin so that you have absolute zero down at the right spot. Okay, this equation we're not going to worry all that much about, but we'll play around a little bit with linear expansion. One last topic, relative humidity. When we talk about humidity, we're usually talking about relative humidity, and that is at the top end of the scale is the absolute maximum amount of water vapor that given the temperature we're at, that the air can handle, right? Absolute maximum water percentage of water in the air, or amount of water in the air. And when we talk about relative humidity, we talk about percentage of that. So here today in Cleveland, relative humidities, I don't know, I haven't actually looked, 65% or so. That means we're at 65% of the maximum amount of water you can put in the air before it simply starts falling out of the air. All right. This is an important distinction to realize, because relative humidity is the biggest contributing factor to what temperature we seem to experience. So this gets us to, how do we experience temperature? And the reality is, we don't experience temperature. What we experience is heat flow in and out of our body, not temperature itself. So when the relative humidity is high, that means there's a lot of warm water vapor. It's at air temperature. It's not any hotter than the air. So let's say it's 95 degrees Fahrenheit. That means, and the relative humidity is high. That means there's a lot of water vapor in the air that's at 95 degrees Fahrenheit. That means the heat that you're trying to shed, right, has to work against all the water that's in the atmosphere to escape through, usually we evaporate water off of our skin to shed heat, right? And so the water that we're trying to evaporate off is competing with all the water that's already in the air, and the water that's already in the air makes it harder for the water to escape our body. It makes it harder for, it makes it hard for us to evaporatively cool, makes it feel hotter because we can't shed the heat, and it makes us feel like we're sweating more, although we're actually, well, we're probably sweating a little bit more. But we sweat when it's dry. We sweat in the desert, but we don't have sweat all over our clothes because it evaporates right away. All right? So when we talk about the temperature that feels like, it's all because of relative humidity and what that relative humidity does to our ability to evaporatively cool. Now, I want you to do something. Now that you know the, among other things, the first law of thermodynamics. Let's find that. Where did I put that? Sorry. Now that you know the 0th law of thermodynamics, I want you to do something. I want you to look around your room and grab up several different objects. All of them, unless it's a cup of hot tea or coffee that you have sitting around, all of them are at the same temperature. But if you grab a ceramic mug that's been sitting out at the same temperature as everything else, versus a plastic solo cup, versus metallic silverware, versus plastic silverware, versus your sheets, versus other plastics, you'll find that they all feel like they are at different temperatures. And what you're really experiencing is, for some of them, heat readily flows from your body into the object, and for the others, it doesn't. All right, that's the end of our segment on heat, and I'll talk to you later.